watch your clock right there.
Would you help me to put this? I cannot see one.
Oh, it's actually over here.
Oh. Good morning. This portfolio entitled Mechanics of Multifunctional Materials and Microsystems actually used to be the Mechanics of Materials program. And when I started working at AFOSR in 2002, and since then we added some new focus. So really the program is no longer a traditional mechanics program. I'm actually quite happy about the resultant outcome of investment made by AFOSR in this area. And all the thanks to the hard work of researchers involved. And for the spring review presentation, I normally give the highlights of select research activity each year. But this year I'm going to do a bit differently for SAB. So this year I'm going to deliver the overall picture of how this program has evolved, and then in which directions existing focus area are moving along, and then finally some of our new program just started. The goal of the program remains the same, and we are trying to promote the basic research for integrations of emerging materials and micro devices into future Air Force system requiring multifunctionality. And here I'm actually using narrow definitions of multifunctionality coined by system community, starting with the battery structure combinations for UAVs, and then load-bearing antenna for the aircraft, and the space mirror, reconfigurable space mirrors. So they are rather narrow, and in this new narrow definitions of multifunctionality implies coupling between structural performance and as needed functionality to deliver dramatic improvement in system efficiency. So this as needed functionality can be electrical, magnetic, optical, thermal, chemical, biological. It's anything basically dictated by system design requirements. And with these narrow definitions of multifunctionality, actually we have to deal with a really diverse range of topics. And then also at the same time, we have to come up with some of a visionary context which can be used as a focus of the program. So that's how we handled. In fact, among several visionary contexts, we tried these three areas. These three areas are basically main focus area. Autonomic system which can sense, diagnose, respond for adjustment with the minimum external interventions. And then adaptive structure which allow the alterations of the shape, functionality, and mechanical property on demand. On demand, that's very important. And then finally, structure integrations of a power harvest, storage, and transmission capability for self-sustaining system. So in fact, these three areas are somewhat overlapping. Some of adaptive structure can have an autonomic feature, and then this both area, many of them requires power constantly, so it has to be self-sustaining system. Now, aside from this focus area, we also have to handle fundamentals of mechanics for multifunctional design. In other words, we cannot rely on traditional mechanics any longer. So it has got to be combinations of continuum mechanics with the electromagnetic wave theory, and even molecular dynamics. And then finally, when I started this whole venture like 12 years ago, there was not many multifunctional structure available. But in 12 years time frame, a lot of multifunctional structures established. So now we are start to worry about manufacturing and durability problem, and also design interface. Because to prevent this new feature we're adding to multifunctional structure shouldn't become defects. So before moving on, let me just quickly point out some of the key facts about autonomic and adaptive structure. Autonomic system is, of course, the concept came from biology. In other words, our biological system has a wonderful feature of these unique functions as a result of millions of years of evolutionary cycle. And of course, best example is our brain, our nerve system, but also we are interested in self-generating function as well as a self-regulating function, because temperature maintenance and then also the prevention of incipient damage is very, very important. So since 2002, this has been actually main missions of this portfolio. In other words, we have been trying to come up with a multifunctional design of autonomic aerospace structure with this bio-inspired function: sensing, self-diagnosis, actuation and reconfiguration, self-healing, and threat neutralization, and self-cooling, thermal management issue, and then finally self-power system aspects. Among them, actually, we made a lot of progress, a lot of breakthrough, except threat neutralization. This is still, I have to work on it. And adaptive structure. Adaptive structure is a little bit more engineering side, origin. What I'm saying is most well-known example is, of course, morphing wing aircraft. You probably heard of. In 2005, DARPA was succeeded in creating, and then basically this morphing wing aircraft passed that flight test. But this is not sudden development. It was preceded by smart wing structure. In 80s and 90s, aircraft industry tried to twist and combo the wings using the piezoelectric actuator. But in DARPA, these first morphing wing aircraft, they gave up to use the smart material. In other words, it was a requirement so stringent. And then after that, there has been a lot of activity in flapping wing, the UAV. And you probably can see in industry as well as the university, a lot of activity is going on. And recently, now they are moving in. Initially, it was just the insect and the bat wing inspired system, but now they are moving into bird wing area. So one thing I have to really stress is they are constantly trying to invoke similarity between morphing wing aircraft and the birds and insects and bats, but actually that's just similarity. In reality is this biological system is much, much more sophisticated than the approach we are taking. In other words, I just borrowed this slide from my colleague who is working in London office. Dr. Greg Abate provided this slide, and he pointed out that bird's body is made of active material. In other words, feathers are articulated and can sense and deformation and strain, and also millions of embedded sensors are throughout the body. And then also nerve system acts as provided strain feedback. And finally, material can be basically, compliance can be controlled and adapted to the condition. So we have a lot of work to do. So this is actually challenge we have. So now in tackling these various requirements from the multifunctional philosophy, multifunctional design point of view, I was very lucky to have series of MURI program, MURI or MURI-like program in 3 years in a row, handling self-healing materials and structure integrated energy harvesting, and then load-bearing antenna. So of course, the old programs are actually concluded. Now some of them are continuing in the form of a single PI grant or STTR, but this definitely laid out the foundations of this program. But also, all these ideas coming from our meager investment of single core grant. Usually, this is a really heart of the program. And then also, I was helped by lab tasks, in other words, PI of lab tasks. Actually, I don't have many lab tasks. I have very few. Reason is, I basically regard them as brain trust. In fact, corporate memory rather than just doing research lab tasks. So with their help, I could formulate all these programs. And then also I collaborated with a colleague in AFOSR, as well as our sister agency, and National Science Foundation, and European Science Foundation, and NASA. And then this program, 3 programs, was followed by various initiatives. Especially most important is a MURI program 2009 on neurological system-inspired sensory network. In 2012, I could set up a Center of Excellence, jointly funded by AFOSR and Munition Directorate on high-rate physics. Apparently, this is not really truly my core area, but somehow John Fuller remembered my research work done at Penn State before coming AFOSR, so I was drafted. Now this center was moved to the Dr. Jennifer Jordan's portfolio in dynamic materials and systems. And then 2012, we also had this BRI program. I collaborated with Hugh DeLong. So Hugh, we actually created 2 mini MURI-like programs. One of them belonged to Hugh's portfolio, emphasizing bioscience. Mine is emphasizing transducer materials area, the use of a biomolecular material as a transducer material. And then finally, this year, I'm delighted to have this basic research initiative on morphing system. In fact, this is the result of a collaboration between me and 4 program managers, especially Doug Smith in the fluid mechanics area, and then Pat Brashaw in sensory information system area. And then also I had a great help from Greg Obate on bio-inspired flight area. So funding trend. I'm going to actually maintain the current pace of funding, first 2 areas, fundamental mechanics and then design of autonomic structure. And then adaptive structures, and then manufacturing and durability area, I would like to actually increase the funding because these are probably more urgent. And then also probably eventually we may have to shift central focus of this portfolio from autonomic to adaptive side. This is probably a more complex problem, is really very attractive to me. But to make a room, I may have to reduce funding in this energy area. Part of the reason is actually DOE and ARPA-E now started to invest in multifunctional structure with a structurally integrated energy harvesting and storage capability. So basically, I can yield this area. Now, I'm going to skip this because of the limitations of time, but there are a lot of interesting sub-areas actually we had to define. In fact, each of these small worlds, I don't mean asking you to read this, but these are all really breakthrough area, especially like the last one, 3D, the printed composite. Even they are now moving into 4D, 4-dimensional by using tray memory material, but I'm not going to include in today's presentation. And then just skip this transformation opportunity. I'm sure you can imagine what kind of transformation opportunity all this area just by reading the title of each area. And this one, of course, we are not the only one. Air Force is one of the DoD agencies, although we are the lead in this area. But so other agencies are interested, so we are actually holding the workshop. A tentative title like this second multifunctional. So every other year we are holding in conjunction with my program review. In 2012, I held second multifunctional materials for defense workshop, and in collaboration with my counterpart, the ARO and ONRs, and representatives of Air Force Research Lab, various directorates, and then 2 directorates of Army Research Lab, the weapons and materials and sensors, and the Naval Research Lab. So we held this workshop, and we intend to hold the 3rd one this summer in conjunction with my program review. Also, I had a very close relationship with NSF. In fact, this whole sensing area was started by, this whole initiative was actually influenced by this initiative proposed by NSF people. And then after he retired, now I'm trying to organize some of a collaborative relationship with my direct counterpart, in fact, the program director in the mechanics of material, and Marty Dunn, who used to be PI of my program. But as soon as he got the NSF, he moved to Singapore to become a vice president of research. They're trying to set up the MIT equivalent in Singapore. So now these days I'm actually talking to his successor, Tom Sigmund. In fact, Tom Sigmund is also one of my PI for the program. So especially in the area of musculoskeletal system, inspired this molting structure and also the regeneration, remodeling area, and we are thinking about. Now for the remainder of time, about we got 20 minutes, that's great. And I'm going to quickly go through some of the key results of these various areas. I selected this area based on one criteria. This area has been sponsored by multi-year, basically I don't know what word I use, multi-year time frame. In other words, it's a really long-term commitment we made in the combinations of a single PI, MURI, STTR, and so forth. So I will go through quickly each area. First, self-healing material. In fact, self-healing materials area actually brought the fame to AFOSR. We are the first one which invested this area when DARPA and NSF declined this proposal. So in fact, I have to give a credit to my two predecessors, the Professor Ozen Ochoa, now back at Texas A&M, and Professor Tom Han at UCLA. They are the one who actually decide to fund this program. So initially, when they funded, that this capsule-based self-healing concept was one of the sensational development. In other words, by putting tiny capsule containing healing agent and then put in the polymer matrix, then when crack comes, then capsule opens and react with the catalyst and heal the local region. And but unfortunately, the size of capsule around when I actually took over this portfolio was about 200 to 300 micron. So you can put it between the ply, but not between 10 micron diameter fiber typically used in aerospace composite system. So I continue to support in the form of a single PI grant, and then last year we finally concluded, now moving into the next stage of a damage tolerance issue. But here, as you can see, this 10 micron diameter carbon fiber now all populated with the nanometer scale capsule containing healing agent. You know, this is a really truly remarkable engineering feat. Reason is, if your capsule wall is not thin enough, then this capsule becomes just like a toughening agent. Crack basically deviated around there, so maybe some toughness increase. But this has to be, thin wall has to be opened up and spilled. And they did that. So now we are actually, we can afford commercial grade composite pre-preg, pre-impregnated composite sheet containing this healing agent capsule. We sponsored the STTR program, just concluded. But another development is that these are one-shot deal. Once crack is healed, then another comes, then there is no way of replenishing it. So because of that reason, we organized MURI program in 2005. In fact, I collaborated with Hugh Long on this, and as a result, they developed a series of vascular system. Just basically try to emulate vascular system present in our biological system. So initially it was a very simple the network, and then getting more and more complex forms, even complex shape. But all these are one of the biggest issues. How are you going to put this in structural grade material? In other words, how are you going to make this network survive the structural loading? And there is a solution actually they came up with. In other words, they put the sacrificial fiber intertwined with the fiber composite structure, and then the sacrificial fiber can be evaporated. This polylactide fiber created for the recycling purpose we are utilizing, and then creating the helical path inside the structural composite. And also we found that, we don't show any all these, the analytical aspect here, but we found that both analytically, experimentally, this helical path actually helps in pumping of the fluid through this path. So it actually helps the situation. And then finally, we also sponsor the work in molecular level type healing. There is a polymer system with a reversible crosslink. So when you use this polymer as a composite matrix, then it's just moderate heating. I'm not talking melting. It's basically just very moderate heating, then basically this crack disappears. So this is another approach. So you could put in this heating patch, or you can use this material as a matrix for composite, the carbon fiber composite. And then carbon fiber composite typically heats up when you transmit electricity. So this can be another solution. So these are really whole areas I'm quite happy about. Now probably you noticed that this self-healing is basically, we took a cue from skin healing, because we are dealing with incipient damage, very tiny damage we are worrying about. And then if you look at this diagram, there are of course like microvascular type supply of this basic healing agent, but look at this scab. There is a relatively large scab is formed, and then basically providing maneuvering room. You may wonder couldn't we basically simulate this? Yes, we could. In fact, this particular example, this impact damage, almost as large as a 1/4 inch diameter, like bullet hole. They came up with the solutions of forming scab-like material. In other words, normally healing reaction is from liquid to the solid, very instantaneous reaction to ensure self-healing. But here they created by healing chemistry. So basically they first form the gel and then solidify. So because of gel type reaction, you could fill out this hole as large as a 1/4 inch diameter hole. So in this self-healing area, I think we basically resolved most of the issue. I think remaining issues are probably now we have to really render all this whole area to 6.2 area so that they can utilize the results of we generated. So now we are shifting to more tough problem, more structural side. So in 2012, we held a workshop in US-Europe workshop in Venice, and the reason was Max Planck Institute in Germany is actually ahead of this bone remodeling area. So we held a workshop. So as a result, I drafted Muri topic this year. Part of the reason is not only their work, also I spotted one YIP grant, young investigator from University of Texas, Dallas. He actually initial results showing that piezoelectric phenomena is partly responsible for this bone remodeling. Bone actually under stress becomes stronger. So he actually showed some of the results. So we are definitely trying to combine that new inputs. Now, the self-healing materials area I've been talking about, those are basically, I didn't show the detail, but it requires a pumping. In other words, pumping means basically you need a power. So that's how I got involved in self-sustaining structure. But plant side, there are entirely different vascular systems was developed. Can you imagine that this transport to water, tall redwood tree, all the top instantaneously? That's a remarkable feat, and then they are doing it as a strictly passive means. There is no pumping anything. How they do? They are using thermodynamic trick. They are utilizing this water, in other words, so-called, I think I saw that, yeah, I put it there, yes. They actually utilizing water in metastable state, and then basically the water become tensile mechanical elements, and that's how they extract the water from the roots and then evaporate water through the leaves. And then in summertime, when you visit the forest, sometimes you hear that the clicking sound. And the reason is some of water pressure near the end of the leaves become too high, then it become cavitate, evaporate, vaporize, and that's what you are hearing. In fact, I remember that some of the paper, by measuring acoustic emission, they could accurately define the rate of evapotranspiration. So this remarkable feature, I actually funded this program. In fact, it's a little bit edge of my program, but I funded the program for the team organized by Professor Abe Struck at Cornell engineering team, and Professor Michelle Holbrook in Harvard in plant science side. So it's a little bit more chemical engineering, but anyway, I funded it. So then last year I renewed it to move on this. In fact, all these plant physiological, these results to move to the development of a device area. Here, they actually try to create artificial, superheated loop heat pipes, and then using 2 nanometer diameter, it's a pore, it's a nanoporous silicon membranes, and then try to create artificial roots, artificial leaves, and artificial stem. And then they put these MEMS pressure transducer. They could even monitor that pressure buildup and then basically cavitate. As you can see, this insert is showing some of the cavity formed. And then also they also observed that this how cavity is formed. Another example. I just showed that basically mammal-inspired healing, vascular network for healing and cooling, and also plant mimetic, the cooling concept. Now these are entirely different region, and it's a different application by using vascular system. This is a reconfigurable antenna. There is a connection actually. When I gave this grant to Texas A&M, PI was Dimitri Lagudas. He spent his sabbatical at University of Illinois with Scott White, and he got the idea. So he decided to use vascular system for antenna area, and then eventually he moved out, and the young faculty took over. Now program has expanded and renewed. So now we have 3 universities are involved. And here what they did, these are first actually, but these are much more complicated, but what its principle is, all these liquid metal means ferroelectric particles suspended in polymer, and it was located in this reservoir. So in this configuration, basically frequency of this antenna system is ISM band about 2.4 gigahertz. But when you push down, pressurize, then basically the liquid metal is pushed out these new slots, and then this frequency is shifted. So now it's a GPS band, so without altering any location. So one of the first crude type, but one of the first examples of a reconfigurable antenna. And then moving on to the sensory network. Sensory network, we had this MURI program. Now this year is the last year, so we had a lot of development. I'm sure that you are all aware of that. Our nervous system is a wonderful, the autonomic system consisting of all these millions of neurons acting as sensors and actuators and then data reduction system. And also they can handle large number at the same time. Even they can actually damage tolerant. Even some to a certain extent it is healable. But a really interesting feature is this synapse. When information was transmitted from one neuron to another, it actually relies on combinations of the digital signal, digital pulse, and then analog, basically analog case of a neurotransmitter chemical. So when this one neuron, so-called presynaptic signal arrives next, then it actually triggers the electrochemical reaction in synapse, and in turn it's creating so-called postsynaptic current. So basically, cumulative signal is filtered through this already preset synaptic value. Then once it becomes, then it actually postsynaptic current is transmitted to the next one. So basically, it's a filtering mechanism. In this MURI, there are many achievements, but two most important one is we could create this network of sensors all interconnected. By connecting these piezoelectric transducer by microwire and stretchable matrix, and then as you can see, this small tiny scale can become stretched this large, from 1,000%. Initially, we worried about maybe this possible defects, but it worked very well. So now we can put not only piezoelectric, but we could put some of the temperature transducer sensors. So we succeeded in creating the bio-inspired type of sensor network. But more important thing is we also succeeded in creating synthetic synapse. I mentioned that when the pulse is delivered, then basically it actually creates postsynaptic current. That's exactly what happened. What they did, Professor Chen at UCLA, he actually laid this carbon nanotube on the silicon chip as a channel, and then he put this polymer. It's a hydrogen. You know, last time I had the same problem. Hydrogen.
It's okay, we are not chemists. So.
Yeah. Well, I'm actually simply looking for this sort of hydrogen-rich polymer was added, and the insulators, and then put these of the titanium gold as an electrode. So when there is a positive, the pulse was applied, then basically hydrogen in this polymer layer basically try to activate it, and then attract it to the carbon nanotube, and then created rather electron-rich type of a situation. So that's actually pulse-creating postsynaptic current. So basically, using synthetic material, but we are creating electrochemical reactions and then current. So exactly the synaptic, the function is doing. So at least first step of a synaptic function we could emulate, and then now they are working on creating neuromorphic circuits. In fact, I almost put that slide, but I deleted because it takes probably another time. So, but they were successful. Their biggest problem is power, energy. Silicon-based actually consumes lots of energy. And brain, they never have such a problem. So this is really another the obstacle we have to really overcome. Now, cell power structure. Since we are almost running out of time, so maybe I'll just quickly mention that we had a lot of breakthrough in the multifunctional structure with the integrated energy harvesting and storage capability. Now we are moving on to more selective case of basically putting this solar cell actual micro UAV. In fact, this micro UAV was created by University of Maryland team thanks to NSF support. So we actually provided additional support and putting solar cell, and they actually found that about 15% increase of flight time by covering about 30% of this wing area. So it's quite the encouraging results. And then when all these work, we are just showing that the mostly successful integrations of the solar cells or battery, there is some problem. Reason is, of course, the material tends to degrade during processing, but that's the overcome. We can overcome. But big problem is the thermal mismatch between the device we are putting as a substrate. So as a result, you do have the complex failure patterns, and then especially interfacial area is a big problem. So definitely we need a compliant, strong the interface required. So once again, one of my PI at University of Illinois, Professor Chasiotis, came up with a copper or silicon nanospring. and placed between these two substrate and then embedded device. And initial results are quite encouraging. And then finally, I think I don't have time to talk about that initially, but finally, all these examples I cited, you probably already sense that these combinations of mechanical and the electromagnetic function is creating sort of a multi-physics type situation. So we need really a model. And then I noticed that many of our modeling efforts in the past, there are a lot of work done metal plasticity area, but not much on this functional electromagnetic property area. So Professor Gosh, who used to be Ohio State, he came up with a solution. So even he handled this multiphysics modeling on temporal as well as a spatial basis. So temporal case, they could handle combinations of electromagnetic signal, ultrasonic frequency with a mechanical vibration in moderate frequency, in unify the modeling framework and using wavelet transformations. In the spatial case, he could handle using the so-called asymptotic homogenization technique. So I think I'm done except this basic research initiative. Basic research initiative morphing structure, we are specifying 6 areas, and then 3 areas I just let me just quickly scan through. We are trying to come up with a bio-inspired design of a composite air vehicles, which can deform just like a bird wing by controlling geometry, surface area, stiffness of a skeletal frame with the muscular structure, and especially the morphing joints. So there are a lot of ideas actually tossed. And then there is an active material. In fact, our previous initiative, we came up with a lot of interesting active material, like first ever reversible shape memory polymer, and artificial muscle based on carbon nanotube, and then this self-oscillating gel, and which VIA is currently working on to make this structural grade material, and then some of the proprietary system offered by industry. So we are trying to transform these various input into assembly that basically can modulate mechanical property in reversible manner. And then finally, we are trying to integrate this active material with the so-called computational metal material. This is a relatively new concept, basically computer as a material and material as a computer, so that we can have this periodic material which can sense and actuate based on programmable logic. So this is the main points about this initiative. Of course, the other three areas, sub-area is Doug Smith area, fluid mechanics, and then bio-inspired flight. So with this, I can safely say that programming is a fully focused multifunctional design advanced aerospace materials and structures. And then also major progress has been made in pursuing this vision I presented. And then we have an excellent multidisciplinary research base as a result of our past MURIs and BRIs. And then this year, we are lucky to have this new initiative in morphing structure. And then also, I'm maybe greedy, but I'm planning to 2 more initiatives, one for MURI for the structural regeneration remodeling. In fact, I almost chose title this regeneration remodeling as an immortal material, because you can make a material immortal, constantly replenishing. But it's just too flashy, so I gave up. So, and then next year, hopefully, this mechanical metamaterial for structural damping. In fact, damping area, I feel that we have been neglecting so much, so many years, so we definitely need to invest in this area. Thank you.
Any questions?
Yeah.
Yes.
So you, this is very interesting, the work of the skeletal and the neural. But you don't. I didn't see that you have a model. You need a model that couples both. I mean, you have the skeletal, the muscular, and the neural. So you need, I mean, this is sort of a feedback loop there.
Absolutely.
Yeah.
Absolutely, we need a model, yes.
Right.
And
So I don't think you don't have to focus on that.
you know, trouble is, whenever I prepare the slide, usually this modeling side is, eventually I'm always ended up with just neglecting it, because I cannot put the equation. So, but yes, as a part of our team, we are definitely looking at. In fact, especially when you try to come up with a bio-inspired design, modeling is sometimes really.
But this, in addition to modeling, this coupled modeling, the
Yeah.
neural model, the system, the skeletal, I mean the muscular. And
Yeah. So hopefully maybe I can get help from your portfolio, yes. In fact, I noticed that the name of Professor Oden, so I didn't realize your portfolio is funding that area.
Any other questions? All right, let's thank our speaker again. Break for lunch.
Oh, I didn't know that there is a. See, I could spend a little bit more time there.
I can't hear you.
1 o'clock. We start. Start at 1 o'clock.
Yeah.
It says here.